Okay. How's everybody doing? What kind of questions you guys have? On which sections on chapter 3? I'm gonna email you the exam over the weekend, and I'm gonna try and create as much of the solutions for the homework as I can. I'll pick a few problems out of each section to do just as examples, but in class you have me. I can solve any of the problems you want for you right now. So just ask and I'll be able to answer. Let me know. Say what? Yes, you can take your phone out. Yes. In this situation, I'm okay with it because your textbook is online and you have no choice. The other teachers let you use your phones during class? They don't really say anything about it? They don't say anything about it? Do you learn as much in the classes where you're able to be on your phone? Honestly, do you learn as much? When you're not on it, right? Yeah. You guys are good students, though. Have you noticed your other peers who maybe aren't as good of students? If they're on it the whole time, they're not going to be learning. And, why are you in college if you're just going to pay to not learn? That makes no sense. Got to use your time wisely. Any sections in particular you guys want to go over? Any homework problems in particular you guys want to go over?
We could go over 3.6.
3.6 as a section?
Yeah.
Okay. Limits at infinity. Remember, a real value function f that maps the reals to the reals by the transfer principle. That implies f of this is defined. This is a hyperreal number, and you can evaluate hyperreal numbers. Okay. We say that the limit x approaches infinity of f of x, if it equals some L, if it renders some real result L, for all omega, and we can also say that the limit as x approaches negative infinity of f of x, if this renders the real result L, for all negative omega, then we say that their limits at infinity exist. So here's an example, very simple example. What is the limit as x approaches infinity of 1 over x?
Is the little omega?
Right, we put a capital omega in there for x because if x approaches infinity, it's approaching capital omega. But like you said, that is by definition little omega. And little omega renders what real result?
0.
Yes. So as x grows infinitely large, 1 over x goes basically towards 0. Here's another example. The limit as x approaches infinity of 2x plus 8 all over x cubed 4x plus 2. So we plug in a omega in for all the x's we see, capital omega. Then we approximate. All right, moving that calculation over here. Canceling out omega, we get this, right? But as you know, this is this, which renders what real result? Yeah. So in all these cases, the infinite limit exists, and it is equal to 0. Now, what about the limit x approaches negative infinity of that same function? What happens here is you put in a negative omega. Here's what we get. Then we approximate. Okay, and then we reduce this to these negatives cancel, don't they? Yeah, you get the same answer because this equals this, which renders the real result 0. Now, graphically, what does all this mean? Graphically.
At 0, it's discontinuous.
Well, at 0, what do you mean it's discontinuous at 0?
Yeah, like there's kind of like a hole in the graph.
Not necessarily, because if you evaluate f of 0, notice you don't get that. You get 2 times 0 plus 8 over 0 cubed plus 4 times 0 plus 2. This is 8 over 2, which is a 4. No hole there, right? This means when you plug in really large values, the function asymptotically approaches 0 in this case. So in the example of f of x is equal to 1 over x, this is what this function looks like. That's what f of x looks like, 1 over x. And we notice that there's a horizontal asymptote at x equals 0. Let's do a similar limit, and we'll find a similar horizontal asymptote, and then you're going to see what's going on even more. So about the limit as x approaches infinity of this thing. Here's what we get. Here's what we get. This renders what real result? Yes. So the limit as x approaches infinity is 2. Notice what this means is, it's just like that graph, but 1, 2. This thing will look like 1 over x, except it's going to be shifted up vertically by 2 units. And notice that this function towards infinity here gets really close to 2, but never touches it. That's what that really means. So when you take the infinite limit and you get a value, this is equal to your horizontal asymptote. This is a very important concept. This will be on your test. I will say, find the horizontal asymptotes of a function like this. And you're going to know that means I need to take the limit at infinity. You also need to take the limit at negative infinity. Will there be any difference here?
No.
No, because there'll just be a negative here, and it still reduces to 2. That's why I had it this way. But not all functions are like that. Let's see an example of one that's not like that. Also, you're not guaranteed to have a finite infinite limit, right? What about this guy? Which reduces to what? Yes. Negative, which equals what?
No.
It's cubed.
Oh, yeah. Negative,
Do you want to know why?
positive,
Yeah,
negative, positive, and then times negative.
remains negative. Yes,
Yeah.
yes, yes. That's exactly how you think about it, exactly the way you said it. But this renders the real result negative infinity, right? So that's why f of x is equal to x cubed. That's why it looks like this.
So that graph, it's supposed to look like that?
Yeah, this is f of x is equal to x cubed right here. Notice that as x grows large, so does f of x. Right?
You don't get an asymptote with that one?
Not really. Not really. There is no asymptote. This thing just grows without bound. It doesn't approach a value. Now, what if I had this situation? 1 over x cubed.
Okay, over there you should get an asymptote. Like this. Oh, yeah, because it should be 0, right?
Right. So this renders the real result 0. Now, what about this? Negative infinity of 1 over x cubed.
Would still be
Yes. They both render the real result 0.
That one would make an asymptote, right?
Yes.
Zero.
It'd be an asymptote on the x-axis.
Okay, so whenever the limit it's like positive or negative infinity, it's just like kind of like going up, right? So for example, because the one that you graphed over there, that's for whenever it's positive, right? So if it would be negative, would it be like the other way?
Right here. This would be if it was negative.
Oh, okay, that's the negative one, then the positive one.
Because this is towards negative infinity. Great question. This is towards positive infinity.
And so if we are asked to graph, like let's say the one for positive infinity, do we only like graph only like the right side, or do we also like graph or like draw the left side?
Well, it depends what I'm asking you. What if I ask you, does this function have any horizontal asymptotes? And then I ask you, graph the function. You have to graph the whole graph, right?
Yes.
And then you have to tell me, no, it has no horizontal asymptotes. The limit as x approaches infinity for plus or minus infinity renders infinity. And so the function grows without bound. It's just however big of a number you input, it grows just as big, if not bigger, because it's cubic. So what about this? Where are all the horizontal asymptotes? Of this function? Find the horizontal asymptotes. Actually, I can give you f of x is equal to this. I say find horizontal asymptotes. We'll denote as HA. This implies you know in your brain to say that means I need to evaluate plus or minus this. You need to take the plus or minus limit.
So we do both?
You're going to do both. I wrote them all in one, but you're going to do both. Because sometimes they're different, as you saw with x cubed, right? Sometimes they're the same. Sometimes they're different. Let's see if this one is the same or different. In the positive case, we get this. Right? In the negative case, you get this. So let's see what this approximates to. What does this equal? Yeah, these cancel. Done. What about this one? Let's see, what does this approximate to?
It would be the same.
Yes, the negatives cancel. The omegas cancel, and we get 2 over 3. So what does this function look like? Well, we know at least that at 2/3, there's a horizontal asymptote, right? Now, what if I say find the vertical asymptotes? Because I guarantee you this function also has vertical asymptotes. Where at? Where will the vertical asymptotes be?
Maybe 0?
Say what?
Maybe 0?
-0.
No, maybe 0.
Oh, maybe 0. Well, it does have 0 involved in it. We put the denominator equal to 0 and solve for x. That will tell you where it's going to be undefined if we put a number in.
Oh.
that is where the vertical asymptote will be at negative 2/3. Like that.
So that way, like, we can graph it, right?
Yes. The function is going to look like this. Why does it look like that? Well, think about it. If I input negative numbers, will this ratio be negative? Actually, it won't. So the way I've drawn it, I have to correct it. Because, for example, let's see if we want to see what is the function at negative 2. Well, f of negative 2 is 2 times negative 2 plus a 3 all over 2, or 3 times negative 2 plus 2. Negative 4 plus a 3 all over negative 6 plus a 2. This is a negative 1 over a negative 4, which is equal to a 1 over 4. That's a positive number. But we will note that 1 over 4 is like right here. If this is at 1, 1 over 4 is like right here. So actually the way I had it is fine.
I mean, I guess it makes sense because whenever, like, if you get the number smaller, like the 2 and the 3 are gonna get smaller than 3 and 2, you know what I mean? Like over there, whenever you add them, they're gonna be so small numbers because the x is gonna be small.
Yeah, actually, because whenever you plug in like negative 1, you get 2 times the negative 1 plus a 3 all over 3 times the negative 1 plus a 2. This becomes a negative 2 plus a 3. This becomes a negative 3 plus a 2. This becomes a 1 over negative 1. And that's a negative number. So over here, at negative 1, it assumes the value negative 1. So it does make sense that it looks like this.
Okay, and so you can only have the horizontal asymptote whenever you are doing like a fraction, kind of like equation, you know what I mean?
That's a great question. Can you only get a horizontal asymptote if you have a fractional equation? I'd have to say you are right. Yes.
On the other one that we were looking at, one that only goes up or down, you don't get any of them.
No, because the more you put in, the higher the value gets. And yeah, like you said, in the fractional equation, there seems to be some interplay between the numerator and the denominator.
And what about vertical asymptotes on the other ones? You don't get any as well?
No, because let's say f of x is equal to x cubed. Do I ever divide by 0? Do I ever get an imaginary number? No, I don't take square roots of negative numbers here. I don't divide by 0. Those are the 2 illegal operations in this class, at least. They're not illegal to mathematicians.
So if like the equation was like the square root of x.
Let's do it. You want to do the square root of x?
Yeah.
Let's do it. Do you just want it to be square root of x and that's it?
I mean, if you want, you can add something.
I mean, you want me to add it, or you just want to keep it simple?
Well, what if we do it simple and then we add?
Sure. Okay. Square root of x, what do you want to do with this?
So, like, take the limit.
Okay. Okay, this becomes this. Right? What is that?
Okay, that's equal to like.
What does this render? You got to think about it, don't you?
Yeah.
Well, remember, here's the reals. Here's the omega 1s. Here's the omega squareds. Here's a capital omega. Here's a capital omega squared. Where does square root of omega live?
Between the normal omega and the real numbers, right?
Yeah. So is it at a higher level than the reals or a lower level than the reals? Higher. So square root of omega is like a very large number or a very small number?
Very large.
Yeah.
All right.
That's how you think about it. Now, what about this?
Okay. Will that give you like imaginary numbers?
Oh. Right? But this is this. Which is technically I times infinity, right?
On that point.
Yeah, that's no. We don't want to deal with that in this class. In complex analysis, you do deal with that. Actually, this is complex analysis where we're doing calculus with the imaginary numbers. But in here, we don't get to have that much fun. Seriously. So that's why the graph of f of x is equal to x squared looks like this.
Oh, I got you. So that's how that one, the first one looks like, right? Because you cannot go like lower, you cannot go negative, right? So it starts.
Oh, yeah, great question. So notice this is f of x equal to the square root of x. I can make this happen by saying this is negative square root of x.
Oh,
But notice the negative is on the outside of square root of x, not the inside. There's a big difference. Yeah.
So if like, let's say, so whenever you did that, the one with the negative infinity, so what would you say? Like how, like what answer would you give if like that?
This one?
Yeah.
You say that we stop right here because we have complex numbers involved, and we only want to deal with real value functions. So the limit doesn't exist because it doesn't render a real result. It renders an imaginary result.
So we couldn't graph it.
No, that's why f of x is equal to square root of x. They only graph this much. It goes on forever like that. Now I could have had negative square root of x right here. All of our answers would have just had a negative on it. So notice that this approaches negative infinity as x approaches positive infinity.
Okay, now what if like you add something to it?
You want to add something to it? What do you want to add? You've been such a good student today. I'm gonna let you add it.
I don't know. Like, okay, well, let's say we add like we make it a fraction with a square root.
Oh, that sounds cool. Okay, let's do it. Fraction with square roots. That's a great idea. Also, guys, I haven't. I'm gonna grade your test number 2, while I send your test number 3. So yeah, you will get grades for that. It's not just like forgotten about. So, what about the limit as x approaches infinity of this thing? Well, there we go. How about that? What is the horizontal asymptotes? What is the vertical asymptotes? In fact, what is the domain?
So the domain is, so it cannot be negative, a negative number, and the like bottom cannot be 0.
Right. Notice that this is the same thing as this. Right? Okay, so we say that this thing has to be greater than 0. So you take the square of both sides. Then you solve for the inequality. So we know that the domain is x has to be greater than -2, but not including -2. So that's the domain. That prevents division by 0 and complex numbers. This,
Okay, because if you add the -2, it gives you 0, right? Or not?
yeah, so look,
Mhm.
for example, this says -1 is allowed. If I plug in a -1, that's still positive. We're not taking the square root of negative number. So yeah, we set this denominator greater than 0, remove the radical, solve for x. This is the values that are allowed. Just
Do we
allowed.
also do the one on the top? Like, so the top doesn't equal.
Yes, we have to do the one on the top as well. That's why this is a great example. Yeah. But what was I going to say? Yeah, this is the domain, but the vertical asymptote is when this is not an inequality, it's an equality. The vertical asymptote occurs when that equals this. So then you get, this is where the vertical asymptote is at, right?
Yes.
So far, this is the domain. Now you also have to make sure that 5x plus 1, right, greater than or equal to 0, because it can equal 0. The numerator is okay to equal 0. And then you solve. Yeah, a problem like this will definitely show up on the test. So this says, okay, from this is true. So then you combine this information with that information. And we notice that if you combine that information, we can use a different color here. This information, notice that -1/5 is over here. And that is like this interval allows for here, but not this amount. So we're going to have to forget this amount because even though f of -1 doesn't mess up in the denominator, f of -1 does mess up in the numerator. Notice in the numerator, f of -1, yeah, I know you get it, but it equals this. Right. So then that's bad.
So then the domain would be that one only, right?
Yes. In the yellow. Yes. So that's our domain. We found our vertical asymptote. We found our domain. What is the horizontal asymptote? We haven't found that yet. So let's evaluate this limit here. Notice that this gives us so can you approximate it? Yes, you can. So you approximate this to square root of 5 omega all over square root of 3 omega. Why can we do that? Well, it's because we're not violating the approximation principle. Okay, then we notice that this is root 5 root omega, and this is root 3 root omega. Yes, these cancel. So we get root 5 over root 3, which if you rationalize is like root 3 root 5 all over 3. If you then combine them to this, you can just express it like this. That is your horizontal asymptote for x approaches positive infinity. What about negative infinity?
I think, no, I mean, well, yeah, it could be the same, right? Because you approximate.
Let's put a minus here, a minus here, a minus here, a minus here, a minus here.
They cancel.
Well, yeah, they would technically cancel, wouldn't they?
And so that would be the horizontal asymptote.
Mm-hmm. Yes.
So then the graph, how would it look like?
Well, I don't know what square root of 15 over 3 is. So let's say it's up here. If it's a ratio of two functions and it has a horizontal asymptote and a vertical asymptote, the vertical asymptote was at when we set this equal to 0, which was x is equal to negative 2. It would look like this. It's not going to have negative values ever. So
With the domain, what about the domain? That means like there cannot be any.
yes, yeah, we have to take the domain into account. If this is negative 1/5, yeah, so it wouldn't be defined from here to here. And actually, this part wouldn't even exist either. Yeah. Yeah, that part wouldn't even exist either. But it does asymptotically approach our horizontal asymptote. Like that. Yes. Yes. Isn't that cool? It's just like a step-by-step thinking process. Very good questions. Very good. What else?
What else is on this chapter? Or is this like almost about it?
That is it. It's limits at infinity. We could do different kinds of limits at infinity. But really, it's just plugging in a capital omega and simplifying and rendering a real result. One interesting example in this chapter that I guess is worth talking about since you want to talk about it is how do trigonometric functions come into play? So what is this one? What is this equal to? Then, so this equals this. But what is this equal to? Right,
Yeah, that's a good question.
right. We know sine is bounded by -1 and 1, right?
Mhm.
So by the transfer principle, we can actually conclude this is true. All right. But then when we multiply both sides by 1 over omega, we get this. Right? What do you notice happens? What does this render the real result? And what does this render the real result of?
So little omega.
Yeah, it becomes this.
Little omega is positive.
Yes.
And so we multiply by that because that's our bottom, right?
Yeah, we want to build this function. Because we want to build this function, that's why we multiply by 1 over omega. So what does that render?
0?
Yes, both sides. Isn't that crazy? So what must this be if it's greater than or equal to 0 and less than or equal to 0?
And that means it's a 0?
Yeah, that means it has to actually equal 0. Isn't that cool? So that graph actually ends up looking like this. Isn't that cool? Yeah, actually.
Oh, so like every time, like as it goes like infinitely, it's trying to get to 0? Is
Yeah.
that it?
Yeah.
That's why like it comes from like big to little to like small.
Yes, that's right. There's an asymptote here. Yep.
And so, like you see how it crosses the x-axis, right?
Mm-hmm.
In there, does it have does it have holes or it doesn't?
No holes. We're never dividing by 0.
Oh, okay, gotcha.
That's a good question.
But it's just trying to get over there, like.
Yeah, and the reason that's the case is because this is a trigonometric function, so it's continuous.
Mhm.
This is a polynomial, it's continuous. Ratio of continuous functions is continuous. The whole thing is continuous.
And does that only go this way, right? Like if it was negative infinity, then it would go the other way, right?
That's a great question. Now, it can actually go the other way. Now let's see. What is the limit? As x approaches negative infinity, sine of x over x. Right? Let's analyze it. What does it do to the left? So then again, this equals sine of negative capital omega over negative capital omega. But sine is an odd function. Those, you know, from trigonometry, an odd function, f of x is odd if f of negative x is equal to negative f of x. So sine is actually odd. Because sine is odd, sine of a negative x is equal to negative sine of x. It's very interesting. It's a geometrical implication. But then this equals this then, if that's the case.
Oh, so then can you cancel the negative?
Cancel the negatives and you get the exact same situation as before.
So you would still be positive, right? Because you would get the same answer, right?
Well,
Or not?
well, yes, but that doesn't mean, yeah, it doesn't mean it's not defined for these values. It would just look like this.
It would look like the same, but on the other side?
Yeah.
Okay.
Isn't that cool?
And so is that like, are all the trigonometric functions like odd? Like
Matter of fact, I kind of messed this up. I messed this up. It should look exactly the same. So it should be like a mirror image.
Oh.
It should be like this. Look. Anyways, yeah. What were you asking?
Yeah, so like are all like cotangent, tangent, cosecant, all of those are odd, right?
No, cosine is even. That implies cosine of negative x. Cosine of x. Sine is odd, cosine is even, and that's it. The rest of the trig functions are built off of sine and cosine.
Oh, sorry.
So what about tangent? Is tangent even or odd?
Tangent is the same as sine over cosine.
Yeah. What is tangent of negative x? By definition, is sine of negative x over cosine of negative x, right?
So negative sine of x over cosine of x.
Yes. But notice that that is by definition negative tangent of x.
Mm-hmm.
So is tangent even or odd?
Odd.
It's odd. What about secant? Is secant even or odd?
Okay, secant is it cosine over sine?
Yeah. Secant is 1 over cosine.
Oh, 1 over cosine.
So secant of negative x is 1 over cosine of negative x. But notice that that's just 1 over cosine. Notice that that's just secant of x. So that means secant of negative x equals secant of x. So is secant even or odd?
Even.
It's even. So if it's built off of a cosine, it's even. If it's built off of a sine, it's odd. If it's built off of a ratio of sine and cosine, you've discovered that it's odd.
And so why is that? Why is it like one even? Why is like sine even and why is cosine odd?
That's a great question. And if you had me as your trigonometry teacher, I would have taught it to you a long time ago. But notice that here's what cosine looks like. Here's some x, all right? Well, then here's some negative x. Notice this is cosine. Right here. Notice that cosine of x is exactly at the same height as cosine of negative x. That's why we say that they're equal to each other. That's why it's an even function, because cosine of x and cosine of negative x are actually at the same height. They output the same value. Think about it. Cosine of pi and cosine of negative pi. They're both going to output a -1. But now sine is odd because of this fact. This is what sine looks like. Notice if we come down here at x and we find -x, right here, this is where sine of x is at. But down here is where negative sine of x is at. Or sine of -x, I mean. And we measure that this distance is exactly the same as this distance. It's just going in the opposite direction. So because of that fact, we say sine of x with a negative on it is the same thing as sine of -x. That's why it's an odd function. It has to do with symmetry. Cosine is even because it's symmetrical to the left and the right of its origin, of its y-axis. But the sine function is anti-symmetric. On the y-axis, it's anti-symmetric. That's why. Isn't that cool? Yeah. You should double major in math, and you should double major in math. Do it. I mean, this is why math is cool. It's because it's just really beautiful. It's just really beautiful. If you like realize these things, it becomes really beautiful. What else? I find it cool when the pictures translate to equations. Equations are cool and all, but they're like kind of boring. A picture is kind of dynamic and cool. So the fact that we can, from a cool dynamic picture, create equations that's fascinating. Because when you have equations, you can use all the tools of algebra, which allow you to discover things maybe the picture couldn't. Whereas the picture could allow you to discover things that the equations couldn't. It's like really cool. What else? Oh, when is this class over? 12:50? Oh yeah, class is over. There is no what else.